What's up, y'all? I've got a question here from Reddit user official Anu, and this is coming from the homework help subreddit. His question says, or their question says, for a differentiable function, the line tangent to the curve at x equals a is used to approximate values of the function near x equals a. If this technique overestimates the correct values, then the curve of the function at x equals a is blank, and we can choose from these values or these options of negative, rising, falling, concave up, concave down. Okay. In the title of the question, the user also asks, what does it mean by overestimate? And that's actually, I think, really the key to understanding this. So I posted our little question here. So let's draw some axes. I'd started working on this and then I made a mistake. So I'll just do it again. Oops, we don't want to erase. All right, axes. Okay. Here are some axes, and we have just a generic function here. I don't know what this is. It's a function. And then at some point x equals a, we have a tangent line. So let's call this point here. That looks approximately tangent. Okay. So what this is saying is here we have a value x equals a, okay? And then we go over and we have a value f of a. Now, we're going to use this tangent line that we've drawn here to approximate the function value near x equals a. So let's say that this value here, okay, is x equals a plus delta x, okay? So we are going to go up to this line, and this is going to be our approximation for f of a plus delta x, okay? But this little distance here, and let's blow it up. We've got really sloppy. So here's our curve, and then let's use the ruler since I can't draw straight lines to save my life. Okay, and I'm going to even change this a little bit so it's more pronounced. So here's, okay. So this is a, or I should say f of a, okay? And here's f of a plus delta x, and then here's our approximation of it, all right? So this, because our estimate is above the actual function value, or the correct value, as they say in the question, is an overestimate, okay? We're going to call this epsilon. That could be our error, all right? And that's just an expanded version of this. Now, as we're very close to x equals a, if our delta x is small, you can see that this error is very small. So it's like a nice approximation. But what does this mean in terms of our question? Okay, it says if this technique overestimates the correct values, this is what we have depicted here, an overestimate, then the curve of the function at x equal a is negative. Is the curve negative? Could we have an overestimate here? If this is x equals a and we draw a tangent, let me use the ruler. Ugh. Can't draw straight lines. It's just not possible. That's why I really love this sketchbook. So can we overestimate when the curve is negative? Sure. Can we overestimate when the curve is rising? Yeah, it's rising here. Can we overestimate when the curve is positive? Sure, absolutely. We started with that example. Can we overestimate when the curve is falling? Sure, yeah. we absolutely can overestimate when the curve is falling. So let's see. We could do that at this point here. All right. So what does this actually mean? It means it's concave down. It means that for this value A, the slope is positive, right? But the second derivative is decreasing. Okay, we have downward concavity here. That's the only condition that this will happen consistently with. So here you can see the counterexample, right? Let's bring our little ruler over here. Okay, so the concavity switches about here. It looks like. So if we use f prime, let's call this f prime of b. Okay. This point, this is x equals b. X equals b. This is f of b. Okay, and this line is the tangent there. Well, this is an underestimate. This epsilon is an underestimate, and because our estimate is below the curve, and what's happened here, we have concave up. Okay, so E is the correct answer. E is the correct answer, and I hope this helps. You know, I don't know if my explanation is going to give you a better understanding of this. And I really don't like to think in this pictorial fashion, but I think that's going to be the clearest way to get the message home to you. Maybe we can give like a nice definition of concavity, and that would drive it home, but I think that would take a lot longer and doesn't necessarily give you a good intuition. You would have to still imagine that for a while before you got it locked into your brain, so to speak. And this will work. If that helped you, please give me a subscribe, comment something, let YouTube know that you love it. Post more questions, go to my subreddit, look at my post history. I made a subreddit a few days ago. Post them straight there and I'll make you another one of these. And tell your friends. If somebody's struggling in class, I can probably help with most math things you would encounter in your undergraduate degree. So thank you.